Alright, we're in unit number 4. And the title of unit number 4 is Force and Motion. So this chapter is all about forces. And when we talk about forces, we're talking about Newton's laws. So Newton had, well, he had a lot of laws. But the three that we're going to take a look at are the 3 to 4 main ones that he came up with. So the first one, which is inertia. Second one, which is best described by an equation, F equals ma. It's really has to do with acceleration. And then the last one deals with action and reaction. So we're going to do forces of motion. This is about an 18-day chapter in terms of just number of class days, including a lab on friction. And before we actually kind of jump into Newton's laws, we have to give you some background. We need to define force, and we also need to tell you a little bit about balanced and unbalanced forces and make sure you understand the difference between them and what balanced forces, what unbalanced forces can cause and what unbalanced forces do not cause. So here we go. All right, so the first thing we need to do is we got to define what a force is. And anytime you hear someone say, "Hey, I exert a force," a force is either a push or it's a pull. It's one of the two. And so anytime you push something and anytime you pull something, we classify that as a force. So we'll put down push here and pull right there. So push or pull. So the force exerted, oh, this is something else you need to know. The force exerted in a rope, string, or chain. We're going to use that kind of all year long. So when you hear, like if I, instead of pulling on something, like grabbing someone's shirt, I could maybe wrap a rope around someone, pull that rope, pull that force that's exerted through that rope, we just give it a name, and it's called tension. So you just need to be aware of that, and when it comes back up, I'll remind you as well. Okay, the next thing we need to know is net force, and net force goes by a couple different abbreviations. This is the Greek letter sigma. Maybe I can zoom in a little bit more for you. So that's the Greek letter sigma. So and the Greek letter sigma means sum up. So you're going to sum up all the forces, and also the net force is Fn, F sub n. And the net force is this. It's the sum of all the forces acting on one object. The net force is also known as the resultant. And we've talked about resultants before in a previous unit. So that should be familiar. And to understand what net force is all about, I've got 1, 2, 3, 4, 5, 6 examples. And this is example number 1. In this one, we're going to have you calculate the net force acting on each of the objects in each example. These aren't too tough. Don't make these difficult. How about I do this? I'll do the first 1 or 2 with you, and then maybe what you could do is stop the video with. I'm yawning. You need to stop the video and try the rest of them on your own, and then you can verify it after you're done. So here's the first 2. If you notice, I've got I'm not sure if you can really see it, but I've got an object there in the center, and we've got 5 newtons pulling up and then 2 newtons pulling down. So it's almost like a tug of war. And since they're pulling in opposite directions, they subtract. So if you subtract them, we have 4 newtons, and then you also need to put up. Remember that force is a vector, and since force is a vector, we're going to have direction. So we're going to put 4 newtons directed upward. All right, the next one, I've got 2 newtons to the left, 2 newtons to the right, 5 newtons up. Well, these two, like a tug of war, cancel one another out. So those undo each other. And the only thing left then is 5 newtons up. So this is 5 newtons up. All right, if you want to stop the video, try C, D, E, and F on your own. Okay, here's the answer for letter C. The answer for letter C is going to be C. We have 5 newtons up, 5 newtons up. So those two together gives me a total of 10 up and then 10 down. So those kind of all cancel out. So that'll be 0 newtons. When it's 0 newtons, you don't necessarily need a direction on there. Okay, number 10. We've got 3 down. I'm sorry, 3 up, 3 down, 5 left, 5 right. So they all cancel each other out. So that gives us 0 newtons again. Okay, let's see what's going on with this one. I've got 2 up, those 2 guys, I got 2 down, so those 2 cancel out. 2 left, and looks like 3 right. So 2 left, 3 right. So that means that we're going to have 1 Newton extra to the right. Okay, the next one's maybe a review from last chapter, or the last unit. These 5 Newtons down cancel out 10 of those, so you could almost do something like this. And so you know the resultant it's going to be something up and to the right, something along those lines. Now, right now I'm not too concerned that you actually do that. We have done that in the past. We did that, I think, in unit number 3. Whew, I yawned again. Unit number 3. But that's where you would, remember doing this? Sum up all the forces in the x direction, sum up all the forces in the y direction, list them all, do sine and cosine and tangent. We're not, you don't need to do that one on there, but I would say up and to the right. And obviously, if this were a test question, we'd want you to actually calculate that, but we're not going to worry about that in video time here. Okay, the next page. Example number, page number 2. We need to walk you through balanced forces. So how about we give you the definition to balanced forces, and then we'll run through the examples. So balanced forces is when the sum of the forces, we now have a name for the sum of the forces, and that's called the net force, acting on one object equals 0. So if everything zeroes out, we call those balanced forces. So which of the above examples is an example of a balanced force? So if we go back here to the previous page, which ones are balanced? Well, that would be C and D, because both of those have no net force. They're both 0 in those cases. So we'll say, come back over here, and we'll say B. What did I say? I totally forgot. C and D. So put down C and D. Okay, the next one. The acceleration of an object whose force is balanced is 0. So if everything's balanced out, you won't be speeding up, you won't be slowing down, you won't be turning. Everything zeroes out. Everything cancels out. So it'd be no acceleration. Balanced forces yield no acceleration. These are all from the departments, the redundancy department. The acceleration of an object when the net force is 0 is 0. So if everything's 0, or the net forces are 0, or everything balances out, then there's no acceleration. True or false? An object will either be speeding up, slowing down, or turning if the net force is 0. Well, it will be, let's see, an object will either be alright, if it's 0, if the net force is 0, it's none of those. It won't be doing any of those, so that will be false. It won't be speeding up, it won't be slowing down, and it won't be turning. So if everything's zeroed out, then you basically have constant velocity. And we'll get to that. All right, example number 2. All right, 2 painters, one with a weight of 120 pounds and the other with a weight of 180 pounds, paint on a platform, which is 100 pounds, supported by 2 ropes. What's the tension in the rope if each rope is the same? All right, let's define tension real quick. We've already talked about it. So tension is another term referring to a force that's exerted through a rope. That should be a string. That's a typo. A string or cord. All right, so let's see if we can set a diagram up here and see if we can answer this one. So here's the plank, and it looks like there's 2 ropes. So we'll put a rope here and the rope here. And it looks like there's 2 painters. So we'll put 1 painter here and 1 painter here. And I'm sure that they are both saying I love physics. And then let's see what we got here. So 2 painters, one with a weight of 120 pounds. So weight's down, so we'll say 120 pounds. And the other with a weight of 180. Paint on a 100-pound platform, so the platform's 100 pounds. So I'll have that one going down. Supported by 2 ropes. What's the tension in the rope? All right, so let's figure this out. if we're assuming that the painters are at rest, that means they're not rising, they're not falling, they're not doing any kind of acceleration, they're just there. And if they're just there, then all the up forces have to equal all the down forces. That means everything's balanced. So if everything's balanced, then we can say how much are down. So I got 100, 120, 180. It looks like there's a total of 400 down. So if I have 400 down, then I have to have 200 up. Well, then these two together, added together, have to give you 200. So we're going to put 200 here and 200 here, and that's your answer. So 200 up in each case. So knowing just a little bit about balanced and unbalanced forces, we can learn a little bit about what's going on in a particular problem. All right, the next one, unbalanced forces. When the sum of the forces, or net force, acting on one object does not equal 0. So if everything cancels out, then we can say that, if everything doesn't cancel out, then we can say that the forces are unbalanced. So if we go backwards, which of the above examples have unbalanced forces? So if we go back here, so that'll be A, B, E, and F, because those are the only ones that didn't equal 0. So what did I say here? I said, see, A, B, E, and F. All right, the acceleration of an object whose forces are unbalanced is not 0, not equal to 0. That means it will be accelerating. So that's a big thing. If you're going to pick anything up in this chapter, that's pretty much what you need to pick up. If there are unbalanced forces acting on an object, that means the object will be accelerating. There will be some sort of acceleration. So unbalanced forces yield accelerations. Net forces that are not equal to 0 yield accelerations. These are all from the department, say the redundancy department. So this is a big one right here. An object whose forces are unbalanced is that object is accelerating, and it'll be doing one of three different things. It'll either be speeding up, it'll be slowing down, or it'll be turning. And there it is. On the next video, we'll start with Newton's first law of motion.